How's it going? Our goal today will be to find local minimum and maximum values, and this will eventually lead up to sketching the graphs of functions. That is really the bigger picture here. We want to build up to the point where we can use the derivatives to help us to figure out what the graph of a function is going to look like. Before calculus, if we wanted to sketch the graph of some weird function, like I'm just going to write this off to the side, f of x equals x squared times ln of x, we would basically have to make a table of values to get a rough idea of how the graph would look, where it's increasing, where it's decreasing. But this never actually told us where the local minimum and maximum values were. When we would graph functions with just a table of values, we had no way of knowing precisely where the graph would turn, where it would change directions from decreasing to increasing. But the ability to find local minimum and maximum values is going to tell us exactly where this occurs, and this is going to help us sketch more accurate graphs. Now, in an earlier lesson, we saw how the derivative of a function is used to find critical numbers, which tell us where we might find local maximum and minimum values. Today, we're going to see how we can also use the derivative to determine if these critical numbers are going to give us local minimum values, local maximum values, or neither. And to do that, we need to look at a little theorem. This theorem says that if the derivative is greater than 0 on an interval, which means if the derivative is positive on an interval, then f is increasing on that interval. And if the derivative is less than 0 or negative on an interval, then our function is decreasing on that interval. And I think that's pretty intuitive, right? If the derivative is positive, that means that the slopes of the tangent lines are all going to be positive, means the instantaneous rate of change is positive, so that is a function that is growing. And then similarly, if the derivative is less than 0 on an interval, then of course it has to be decreasing because the rate of change is negative. The slopes of the tangent lines are negative. All right? But knowing this helps us get an idea of what a graph is going to look like. So let's take a look at an example. And our example is to find where the function f of x equals 3x to the fourth plus 4x cubed minus 36x squared plus 5 is increasing and decreasing. To do this, we need to see where the derivative is positive and where the derivative is negative. So of course, we're going to have to find the derivative, f prime of x. If we differentiate one term at a time, the derivative of 3x to the fourth is 12x cubed. And then we have plus the derivative of 4x cubed is 12x squared. Then minus 72x. And the derivative of the constant term is 0. And we can factor this, which is going to be helpful in just a moment. First, we can pull out 12x. That is the GCF of the three terms. That leaves us with x squared plus x minus 6. And we can factor that trinomial into two binomials. We need two numbers with a product of -6 and a sum of 1. That's going to be +3 and -2. And before we see where it's increasing and decreasing, I want to look at the critical numbers. Those are going to be where the derivative is equal to 0 or undefined. Now, it's never undefined, so let's set it equal to 0 and solve. If we want to know when this function equals 0, we need to look at each of the factors and set them to 0. And if we do that, this first factor is going to give us x equals 0 as a critical number. The second one is going to give us x equals -3. And the third one is going to give us x equals 2. So those are our critical numbers. And what I'm going to do is I'm going to graph those on a number line really quick. Let's see, we've got 0, 2, and we want -3 on here. So let's plot those points as critical numbers. We've got 0, -3, and 2. And what's happening here is these critical numbers are dividing up the number line into different sections. And I'm going to claim that in each of these intervals that the number line is now broken up into, in each of these intervals, the function is either going to be increasing on the whole interval or decreasing. Right? If we were drawing a graph of the function, then in each of these intervals, it's either going to be increasing or decreasing. It's not going to be increasing for part of an interval and then decreasing. And the reason that's true is if it were increasing and then decreasing, then we would either have a maximum value, in which case the derivative would equal 0 or the derivative would be undefined, and that would give us another critical number. So if we switch from increasing to decreasing, that can only happen at critical numbers or where the function is not continuous. But this function is a polynomial function. It's continuous everywhere. So we only need to check these intervals, these 4 intervals, to see where it's increasing and where it's decreasing. Now, we could pick a number in each one of these intervals as a test point, and we could plug it into the derivative and evaluate this to see if we get a positive answer or a negative answer. But there is a nicer way to do this that I want to look at. Basically, what we're going to do is we're going to make a sign chart, because we only really care if the function is positive or negative. We don't care how positive or how negative it is in these intervals. We just need to know if the derivative is positive or negative to know if it's increasing or decreasing. And what we can do is we can take each of the factors and set them off to the side here. So 12x, x plus 3, and x minus 2. And we can look at each of the intervals to determine if that factor is positive or negative on each interval. Let's look at 12x. All right, 12x is equal to 0 at 0. And if x is greater than 0, 12x is going to be positive. And if x is less than 0, then 12x is going to be negative. So we know that on these intervals, 12x is going to be negative, and then positive, and then positive. We can do the same with x plus 3. X plus 3 is equal to 0 at -3, which was this critical number. And so when x is greater than -3, it's going to be positive. And when x is less than -3, it's going to be negative. And then our last factor, x minus 2, this is equal to 0 at 2. And so when x is greater than 2, it's going to be positive. And when it's less than 2, it's going to be negative. Now, if you've never seen a sign chart like this before, we're going to do a few, so you're going to get used to it. But what we do here is we've got all of the factors of the derivative up above, and I'm going to put just f prime of x down below. Now, we know that the derivative is the product of these factors. And so if we want to know if the derivative is going to be positive or negative, we can look at these signs that we have in each of these intervals. So in this first interval, we've got a negative times a negative times a negative. That means the derivative is going to be negative. In the next interval, we've got a negative times a positive times a negative. Those negatives are going to cancel out, and we're going to have positive. On the third interval, a positive times a negative is going to be negative. And then on the fourth interval, these are all going to be positive. Now, what does this mean? Remember, our theorem says when the derivative is greater than 0 or positive, the function is increasing. So wherever our derivative is positive, our function is going to be increasing. It's going to be going upward. And then when the derivative is negative, we know the function is decreasing. So down here where it's negative, we know it's going to be decreasing. So the function is going to be going downward. All right. I'm just drawing these little arrows to show if it's going to go up or down. These arrows, I've drawn them to be linear arrows, but the function is not going to be linear anywhere. We know it's going to be curving. I've just drawn arrows because it makes life easier. They're easy to draw. Now, what this tells us, I'm just going to extend this down here because these are all of our critical numbers. If we look at this first critical number, -3, the function is decreasing beforehand and increasing afterwards. Well, that means this has to be a local minimum. If the function is decreasing and then increasing, that's what gives us a local minimum. So we have a local minimum here. And the same thing at 2. We have a function that's decreasing and then it changes to increasing. That is, again, a local minimum. And in the middle here, we have a local maximum because it's increasing and then that changes to decreasing. So we have a local max here. And by looking at where the function changes from decreasing to increasing or increasing to decreasing, that will allow us to classify if a critical number gives us a local maximum, a local minimum, or neither. There are situations, and you will see an example at some point, where it is decreasing on an interval, and then we have a critical number, and then it is decreasing on the next interval, or increasing and then increasing. This is what we see when we have f of x equals x cubed. Just going to draw a really quick sketch. Right? We know that x cubed is increasing, and then there's a critical number here, and then it continues increasing. So we don't have a local max or min here. So it's possible that there isn't one. In fact, we can write all of this out and have all of this info in one nice place. I'm going to put this all right here. You can pause the video if you want to write it down. Basically, suppose that c is a critical number of a continuous function f. If the derivative changes from positive to negative, which we can see down here, goes from positive to negative, then f has a local maximum at that critical number. If, on the other hand, it changes from negative to positive, that's right here, then f has a local minimum at that value. And then finally, if f does not change sign at c, then f has no local maximum or minimum at c. It's like our at y equals x cubed example, where we've got a critical number, but it's neither a maximum nor a minimum value. Now, this video is already long enough, so I don't want to take the time to try and sketch this graph. In fact, later, and not that much later, pretty soon, we've got some lessons where we're going to spend a lot of time going through and using information like this to sketch graphs of different functions. So we will get there. Right now, though, I just want to practice on making our sign charts, looking at the intervals to figure out if the derivative is positive or negative, and then identifying if we're going to have local maximums, local minimums, or neither. And once we build up this skill, we're going to use it later to sketch actual graphs by hand.